In this question number 4, we have the start of organic chemistry. We have halogenal alkanes. 2-bromobutane, so 4-carbon alkane. If I start drawing skeletal formula, because if you know my tutorials, you know that I'm a big fan and proponent of skeletal formulas. So, whatever you do, try to master skeletal formula. Carbon form 4 bond, you have 1 covalent bond there, so there is 3 hydrogen, CH3. Carbon form 4 bond, 1, 2, 3, so there is 1 hydrogen there, and the Br is a branch. Carbon form 4 bond, 1 and 2, so there is 2 more hydrogen there. And carbon form 4 bond, 1, 2, and 3 hydrogen there remaining, because you already show 1 bond forming to the carbon there. So this is a structural formula for these 2-bromobutanes. The bromine is the branch at position 2 there. Now you react in 2 different ways with sodium hydroxide, halogenal alkane chemistry with sodium hydroxide, as you know from my topical tutorials, and those are all entirely free for anyone to view, so make sure you try and go through them. It's hydrolysis, which is essentially the substitution of the Cl or Br or iodine, the halogen, with a OH group using sodium hydroxide in water. What was I talking about? Hydrolysis there, the hydro means in water. So that means aqueous conditions. So this is NaOH in aqueous conditions. For elimination, you need NaOH in ethanol. Both of them, you need reflux as well for your heat. Okay, so it's just the choice of your solvent, water, because you're doing hydrolysis of the halogenal alkane, or ethanol if you want to favor elimination there. So here, when you warm it with aqueous sodium hydroxide, you get an alcohol that can exist as a pair of optical isomers. So these are the enantiomers, the non-superimposable mirror images of each other. They want specifically the name of the mechanism as stated in the introductory organic chemistry. When they produce these alcohol, they are going to undergo substitution type of reaction, but the mechanism is going to call nucleophilic substitution, as the OH minus act as a nucleophile. If you want, you can also, actually you cannot tell whether it's SN1 or SN2, because this thing here is a secondary halogenal alkane. The carbon with the halogen is bonded to 1 and 2 other carbon. While it is easy to say primary halogenal alkane prefer SN1, secondary halogenal alkane is tricky to tell because it's intermediate, so it depends on experimental data, and you will find more of these kind of questions in A2 rate of reaction. Now explain why the alcohol produced exists as a pair of optical isomers. Well, if you replace these with hydroxide and you have to do this with aqueous NaOH, NaOH in water, and reflux, and you get the OH like that. I haven't balanced my equations, but if you have NaOH, then you kick out NaBr. The idea there really is the Br get replaced and substituted with the OH, and you get alcohol there. Now these carbons with the OH, 1 OH, 1 CH3, 1 CH2CH3, and 1 hydrogen. In skeletal formula, we don't show the hydrogen bonded to the carbon. Carbon form 4 bond, 1, 2, and 3. There is 1 hydrogen there. So basically, they're asking you what is meant by optical isomer. That's the nature of this question. Okay, so it has a chiral carbon, and that is not enough. There are 2 lines. Its explanation is not state. So that means the carbon there is bonded to 4 different atoms or groups. It's not always just atoms. In this case, you have hydrogen atom, but you also have groups of atoms like the alkyl, like the OH, etc., etc. This kind of question always try to give you some free marks. 3-dimensional structure. We know that carbon form 4 bond, that is a carbon sp3, 4 bond pairs and 0 lone pairs. So the 4 bond pairs repel equally, and you get tetrahedral geometry. And tetrahedral geometry is 109.5 degree. You have to display it at the tetrahedral center there. So 2 flat line, and then 1 is coming out. This is bolded because it's pointing at you right in the eye, coming up from the screen. This is away from the screen, behind the screen there. And I have to draw the mirror image. So draw the mirror image first before putting anything in. So the wedge one, the bolded one is away from you, away from the mirror. Well, when I say away. What it means, it's pointing at you right in the eye, but it's pointing towards the left. So this is pointing towards the right, but it's still coming out from the screen towards you. And the two flat one, this and these are flat. So this and these are flat. They are mirror images of each other. Now, just because we have done the geometry correctly, we haven't put in the groups yet. So typically speaking, I would almost always put the longest group on top here, because it's easy to write horizontally like this: CH2, CH3, CH2, CH3. We do not have to write CH2, CH3 from right to left, because this is a single bond. You can rotate. You like to draw the mirror image like that? Sure, but you can rotate about the single bond, so there's no difference with writing it like this as well. You should get the connectivity correct. So the next one will be, let's say, the CH3. So things like CH3 will be like that. If you write CH3, that is okay, but your bond is really between carbon and carbon. You should really try to be correct as much as possible. So the bond is between carbon and carbon. The bond is between carbon and carbon. 3 hydrogen. You read it as CH3 like that. Okay. Now to the next one, you also have a hydrogen and an OH. So an OH and OH, and last but not least, a hydrogen. To be honest, does it matter where you put the groups around? It does not matter, as long as you have the projector to the correct position in the mirror image, and as long as you have the 4 different groups as you have seen from this skeletal formula of the product, having replaced the Br with the OH there, because you want the alcohol product there. And this is the chiral carbon bonded to 4 different groups or 4 different atoms there. Now this next bit is basically asking you, when you use ethanolic sodium hydroxide, basically this reaction is elimination. So give the name of the mechanism. You don't really do elimination mechanism in AS that much, at least not in the old syllabus, and also not really in the new syllabus, to be honest. But what you can say is, when you have 2 bromobutane, so I've drawn it slightly differently here, but again we have to put in the lowest number for the branch group there. So you have 2 different carbons here, because you gotta remove the hydrogen from the neighboring or from the adjacent carbon or the neighboring carbon. You cannot remove the hydrogen from the same carbon with the halogen, because you're trying to form the double bond. So this is a CH3 hydrogen. It's different from this adjacent carbon number 3 here, because that would be a CH2 hydrogen. The black color one is different from the green color one, because there's only 2 hydrogen here. There's 3 hydrogen there. 2 and 3 are not the same. This hydrogen black color one and this green color one will not be the same. If I remove from the black color hydrogens, my double bond will be 2 and 3, somewhere in between, and I can have cis and trans isomer. That is your trans isomer. That is your cis isomer, because they're on the same side, they're on the different side. You have geometric isomerism in the AS syllabus. But we have to consider the other product as well, which is coming from the elimination from this green color hydrogen. So what do I get? If I remove from the green color hydrogen, then my double bond is between 1 and 2, terminal there. So that is going to be called, well, there's 1, 2, 3, and 4. So that is your but1-ene. Whereas for the black color one, you will get but2-ene. So one of them is trans but2-ene, the other one is cis but2-ene. All together, considering stereoisomers, because geometric isomers are stereoisomers, and also structural isomer, for which there are no other structural isomer of this. There are 3 possible products altogether. Very common type of questions in multiple choice chemistry as well. And not too surprisingly, they're asking you to draw and name the structure of the pair of geometrical isomers. I literally just explained that. I roughly know how these kind of questions will proceed. And when you have done quite a few papers, if you have gone through my topical playlists, then you will be able to see what I'm talking about as well. You will see that here, they said draw and name the structures. They don't mention display, skeletal or structural. That means could be any form, but not molecular. You cannot write molecular formula. That doesn't show the structure. You cannot write structural formula. Structural formula cannot show the structure. Only displayed, yes, because you want to show cis and trans. Cis and trans geometric isomers, they are stereoisomer. Stereoisomers definitions, same molecular formula, same structural formula. You try to write differently, they will have the same structural formula. You cannot show the difference at all. So you can only do display, or you can do skeletal. Both of them are acceptable here to show cis and trans, and I already named it previously. They are trans butene because you want the lowest number, 1, 2, 3, 4, which is the same as 1, 2, 3, 4 trans because they are at opposite positions on that carbon there. On the other hand, that is your cis butene. So this one is these are your geometric isomers. So they have a carbon-carbon double bond. First condition. Second condition, they must not have the same group on the same carbon, must not have the same group or atoms on the same carbon of the carbon-carbon double bond. This is the hydrogen, this is a methyl, this is a hydrogen, this is a methyl. They are not the same, they are not the same. Obviously, you have cis and trans geometric isomers there. Now you want the third alkene. I also did that. And they ask you why it doesn't show the cis and trans. So basically, in the previous question, I already explained what gives rise to cis and trans. So, we are trying to explain why this one doesn't give rise to cis and trans. If you draw this, you don't get the mark because they're specified on name. But I draw it so that I could name it properly. So it's built one in. That's the first bit of the question. The second bit of the question, why this one does not show geometric isomerism. So on one end of the carbon double bond, even though you have carbon-carbon double bond, but on one end of the carbon-carbon double bond, I'm looking at this CH2 double bond. CH2 double bond, there are two same atoms, or in different cases, two same groups of atoms. Therefore, cannot have cis and trans. The requirement for geometric isomerism is not just carbon-carbon double bond. You must have different groups or different atoms, different groups or atoms on one carbon of the carbon-carbon double bond. So, you cannot have a CH2 on that side there. Even though there's that, you can move it around. You will never get cis and trans if you have two atoms or two groups that are the same on one carbon of the carbon-carbon double bond there. Alright. Now to part B, we're given some reaction scheme here. The best thing to do with this kind of question is to draw and see for yourself. That's always the advice I give for students. So 2-bromopropane, and what we get here is we have done a substitution, and we have replaced the Br with NH2. This is what you call substitution. This is what you call type of reaction. Type of reaction is as stated in the AS Introductory Organic Chemistry syllabus. We don't know what X is, but we can suggest what X is from the next reaction. When you hydrolyze X, you are going to get this thing here, CH3, CH2, CO2H. So you get acid, you get carboxylic acid. That is strange. Don't know what that is. We'll think about it in a little bit. Can we? Oh, hang on. And also that thing there. So you get back this thing after you remove it. So you get an amine and you get a carboxylic acid. You get an amine and you get a carboxylic acid. So amine and carboxylic acid, if you work backward, is the opposite of hydrolysis. It's going to call condensation. Is also another type of reaction in AS Introductory Organic Chemistry. You will get something called amide. So if I think about my amine and my carboxylic acid, 3-carbon carboxylic acid, CH3, CH2, CO2H, and I get my amine, H2N, like that, and that comes from here. So I will lose the OH from the acid and I will lose the H from the amine. So this gives me X being the amide, which is like this, and then I have a new amide bond, which is actually this one. So N and then H and then like this. So this is the amide bond that I formed in reaction 2. So that must be condensation. Condensation with this carboxylic acid, and then when I hydrolyze this amide, then I'll get back the 3-carbon carboxylic acid and these 2-aminopropane. This is called 2-aminopropane. So it's the amine group at position number 2. So 2-aminopropane there. So how about this next thing here? If I look at carboxylic acid, as they want you to think about the reaction form from this main reactant and not from the other products. So looking at the carboxylic acid, which is this propanoic acid, 3 carbon acid, giving you 3 carbon alcohol, 1, 2, and 3. That is propane, 1 all. And then that alcohol there give you something else, which is then substitution at position 2. So I had substitution at position 1. Now I move to substitution at position 2 after I reacted with HBr. So when I work backward, when I go backward, if this is addition, the type of reaction is addition, the opposite of addition, going the other way. So from top to bottom, that must be elimination. Elimination, just like we did earlier, is to remove one of these hydrogen. But this is totally symmetrical. So this is a CH3 and this is a CH3. So removing from this hydrogen is the same as removing from that hydrogen. I could get this. It is the same as this one, which is prop 1 in. And you can do addition reaction. And the mechanism will be electrophilic addition mechanism. And from alcohol to alkene, this of course is an elimination mechanism. Sorry, elimination reaction as well. And then the mechanism will be elimination mechanism as well. So you don't really deal a lot with elimination mechanism in the Cambridge International A-Level, but you do deal with the elimination type of reaction there. We've already kind of reviewed the whole reaction scheme there, what is going to happen. So now state the reagent needed for reaction 1. You just need to hydrolyze. This again is hydrolysis. So you need to break the carbon-bromine polar bond, delta plus, delta minus. And you have to replace it with NH2. So it is not hydrolysis, I beg your pardon. Hydrolysis will produce alcohol, like in the previous question, using aqueous NaOH. But here, you want to get NH2. So what you need is, you need concentrated NH3 or con NH3, and this is in ethanol. The solvent is very important. You don't deal it in aqueous solution, you deal it in ethanol, so that you don't have the competition for hydrolysis or for any sort of substitution with the OH from the water at all. So con NH3 in ethanol, and usually you heat in a sealed tube, but they don't ask for the conditions. Otherwise, the condition will be heat in a sealed tube for high enough pressure. State the condition for reaction 2. This is a condensation reaction, and I knew the reactant when I work backward by hydrolyzing, well, by condensing these two products together between carboxylic acid and amine, and I got this amide where the carboxylic acid will have lost the OH and the amine lost the H, and I get the CONH amide chemistry there. So the reagent for reaction 2 has to be CH3, CH2, CO2H. It condensed together with this amine there to give you an amide. Give the structural formula. So here they specifically want the structural formula for X. What I did was I did the skeletal formula for X, so it will not be accepted, but we can very easily have drawn the skeletal formula, and then we read how many hydrogen is here. Carbon form 4 bonds, so we form 1 bond there, so there is a CH3. And then carbon form 4 bond, 1 and 2, so this is a CH2. Carbon form 4 bond, there is a 1, 2 for the oxygen, and then 3 and 4, so there is no oxygen. It is just CO and H. This is the amide, CO and H. And then now carbon form 4 bond, 1, 2, 3, so there's 1 hydrogen there, CH. If we consider this as the branch, then the branch will be CH3, and then on the main chain I have a CH3. So this is a CH. If this is the main chain, is CH3, but then the branch is CH3 there, I put in a bracket there. You could also read from right to left. If you read from right to left, if you go this way, you will have CH3, CH, and then CH3, because this is your main chain, let's say, then this is CH, and then your branch is CH3, and now I'm on the NH, so NH, and then CO, NH, and then CO, and then CH2, CH3. Skeletal formula is the same whether you draw left or right, I guess, but you know, the positioning will be different. They want structural formula, so this black color one is correct. This blue color one will be correct as well. But skeletal formula, it is the correct product, but it will not be credited here because they specifically want the structural formula there. Now part 4, name the type of reactant in reaction 4 and suggest a suitable reagent. There are two types, there are two questions being asked here. Reaction 4 was converting the carboxylic acid into alcohol. To reduce the carboxylic acid into alcohol, you need a very strong reducing agent. Sodium borohydride will not be strong enough to reduce carboxylic acid. You definitely need a much stronger reducing agent, and to do that you need LiAlH4, lithium aluminum hydride. You do this in dry ether, as lithium aluminum hydride is very sensitive to water, and you do need to reflux it as well. Although they don't mention the condition, I usually just include the condition. If you forget it, this is the one that will get the marks, not the condition here. For reaction 5, this is the elimination of H2O from alcohol to give you alkene. You can do this with consulfuric acid as your reagent, but this particular question say what is a solid catalyst, so you can do it via a different method where you just heat it over Al2O3 or SiO2. Typically, we would just use Al2O3. It's just something that would speed up the release of this H2O, the elimination of H2O from alcohol to give you the alkene there. But hang on. I would not get the marks because they want the name. So I should really write down the name, aluminium oxide there. Okay. So they want a catalyst. If you put consulfuric acid there, concentrated sulfuric acid is actually a reactant that is used to kick off the H2O. So actually consulfuric acid will work as well. Yeah. Consulfuric acid could be the answer as well. So you could use concentrated sulfuric acid as well. But of course, that again is formula. They want the name, so that cannot be the answer. You have to give the name concentrated sulfuric acid. So both of them, this one you hit the alcohol, cover in a cotton wool over this particular solid, and you collect the alkene. This one, similar method I guess, because this will remove the water as a dehydrating agent there. Feel this question is a bit long. What do we want? We want to produce 2-bromopropane from Y in reaction 6. Reaction 6 was alkene, prop 1 int, adding HBr onto the halogenal alkane, so it's the electrophilic addition mechanism. So what we are getting there is we are getting like this plus HBr, and then we get this 2-bromopropane there. So we need to complete this electrophilic addition mechanism for alkene. So you can draw structural, you can draw display, you can draw skeletal. So I think, let me just draw display so that it is clear, but you can draw skeletal, there's no problem whatsoever. When I say display, I mean this is going to be structural, partially display I guess, or partial structural. The first thing that will happen is dipole. Dipole, whether this is polar or not, but in this case it is polar, so the dipole there is delta plus on the hydrogen, delta minus on the more electronegative bromine. Rich in electrons from the alkene, not from the carbon, from the alkene, rich in electron, attack poor in electrons, then it breaks the Br hydrogen bond and it will give the 2 electrons to the bromine, and now you will have an intermediate which is carbocation. We could see that we could get potentially two carbocation. Where the hydrogen adds there, I'll get the plus there. But when the hydrogen adds here, I'll get the plus here. I want to get 2 bromopropane, so I want the plus to be there on the carbon number 2, because we are going to form that particular product later on. As the Br now is a negative charge, it has a lone pair, and this from the lone pair attack the carbon. The lone pair doesn't attack the positive charge, it attacks the carbon with the positive charge, rich in electron, attacks the poor in electrons, and now this is carbon 1, 2, 3 or 1, 2, 3. It is the carbon position number 2 with the positive charge that the lone pair attacks and give you this 2-bromopropane. Alright, now give the name of the mechanism. I already talked about electrophilic additions earlier. So we know that this is electrophilic addition, the rich attacking the poor. The alkene is the nucleophile, this is the electrophile. You have done addition of the electrophile onto alkene, is called electrophilic addition there. The very last bit of this whole 22 marks question is this 2 marks question asking you why 2-bromopropane is the major product of reaction 6, but 1-bromopropane is a minor product. This comes down to this mechanism where previously we only show one intermediate because this was the intermediate that will give you this product. So what I could comment on is this is secondary halogenal alkane. So 2-bromopropane. Better spell that properly. 2-bromopropane comes from this cation because the last step was the Br minus attack that bromine there. So the carbon with the positive charge, is bonded to 2 other carbons. There is 1 hydrogen there. So this is a secondary carbocation. Secondary, or usually what I write is 2 degree, that is the short form for secondary, and this is a carbocation intermediate. Now what I can say is 1-bromopropane. So 1-bromopropane, which I did not draw the intermediate earlier, but of course we can still produce it. It's just produced as a minor product. How do you know which intermediate it is? You break away, you try to break that bond there, and then you will get the positive charge on the end there, because the Br minus with the lone pair will attack this bit here and complete the electrophilic addition mechanism, just like it did when you form the 2-bromopropane. The Br minus lone pair attack this carbon in the center. When it is this thing here, the Br minus with the lone pair will attack this carbon and here. So what happened there? What happened there is this is a primary carbocation. How do I know it's primary carbocation? Because the carbon with the positive charge is bonded to 1 other carbon, primary carbocation. Overall, what can we say here? We can say that secondary carbocation is more stabilized compared to primary carbocation, and you have to explain. You cannot just state it's more stable. In fact, tertiary is more stable than secondary, more stable than primary carbocation, because we think about this thing called inductive effect. So there is an effect. If I just put this black color one, the arrow. So I don't like to draw this black color arrow because we are not doing mechanism, but it is showing that you are donating electrons. They are alkyl electron donating groups. So we can say when you are secondary, you have 2 times alkyl electron donating groups. When you're primary, you only have 1. When you're tertiary, your carbon with the positive charge is bonded to 3 other carbons. You will have 3 alkyl electron donating groups. That's why secondary carbocation more stable than secondary carbocation, more stable than primary carbocation. So we need to explain it because there are more alkyl electrons donating groups by inductive effect. Okay, this is as stated in the AS syllabus under alkene chemistry. So the more alkyl electron donating groups you have by inductive effect, you will stabilize the carbocation, which is poor in electron, stabilized by electron donating groups that can help to, help to stabilize these electron deficient, electron poor carbon there. Right? So that's it really. So on the major and minor product, and this is the origin of this Markovnikov rule. Not too sure if they still use this term in the syllabus, Markovnikov rule. But when they say Markovnikov rule, basically that means explain the stability of the carbocation in terms of these electron donating alkyl groups by inductive effect there. 2 marks questions. I have shown some diagram, that's why I'm using up the space. Otherwise, if I'm just using words, I might be able to just use the space within their 4 lines. The end of that 22 mark question there. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. And I'm not sure when the silver tier members only video will be available for everyone to watch, but thank you for supporting my channel. And if you haven't, so do consider upgrading to the silver tier membership for the price of a cup of coffee, and you can get access to all my yearly paper tutorials throughout the channel. And of course, the topical playlists are all for free, and they actually come from the yearly paper tutorial as well, but it's not the complete thing. Thank you for watching. I'll see you in the next tutorial video.